the finite element program, COFE, which means continuum-oriented finite element, and this was programmed by Professor José María Sancho and Planas in 2003. And it implements elements with embedded adaptable crack. It means that the crack is computed according to the principal stress field of the element, and it follows a strong discontinuity theory in which the crack is a jump, is a discontinuity. It follows central force model. It means that the traction vector and the displacement vector are parallel, and there is limited crack adaptability. It means that in the finite element program, the crack orientation is allowed to change until a threshold value WTH of the crack width is reached. For the fracture behavior of concrete in these simulations, we follow the cohesive crack model introduced by Hilbert in 1976, as already explained, and it was applied a recent generalized formulation by Planas collaborators, in which indeed the traction vector can be modified and not being parallel to the displacement vector, but it was implemented just for comparison with other methods found in the literature. But we, for our simulations, for our works, we follow the central force model and values for beta equal to 1. In the calculations, just linear softening was taken into account to speed up the calculation, and because in the study we are just focusing on the maximum of the Brazilian test, and it is supposed to happen for crack openings smaller than W1. So these are the parameters in the simulations. The mesh is generated using the mesh program. You can see that here in all the domain we have elements which are constant strain triangles, all of them crackable elements. So the crack doesn't have a prefix path, at least in this step. So the crack can appear wherever. And for the uncracked material, we assume linear elastic behavior, and for the cracked material, the linear softening I mentioned. Then we apply a band with uniform traction vector, simulating the load in the experiments, and there is a mesh refinement in that zone just to capture much better the crack path. And finally, mentioning that the simulations were carried out under displacement control of the points labeled here as A and B. These simulations were dimensionless. It means that all the displacement, stresses, and geometry parameters were divided by characteristic parameters of the structure. For example, all the stresses are divided by the tensile strength, all the displacement by the characteristic opening W1, and the geometry parameters by the diameter of the specimen. Then from the calculation, there is a dimensionless elastic modulus, which is related with results like that, and it results to be proportional to the breadth length, which was defined previously. So for the size effect study in this work, there are several options. In the results presented here during this talking, we adopted the solution of modifying the elastic modulus of the fictitious elastic modulus of the simulations. So which for a smaller elastic modulus, there is a higher ratio GL1, which implies that the specimen is more brittle. And we covered the ranges studied by Claudio Rocco from 0.4 to 10, just for verification of the method, because as Professor Planas also mentioned in his presentation, the conditions in the simulations were a little bit different according to the available methods in the 90s, and just after verifying that the curves are almost the same, then we enlarge the curves for ratios up to 0.25, which is supposed to cover the current mixtures. These are the meshes used because we considered 4 ratios of bearing bandwidth versus specimen diameter according to the work developed by Rocco. And sorry, I didn't mention that the specimen, the element size was kept the same, almost the same in this band. But the number of elements of the meshes is not exactly the same, so we will improve that in the future, as I will comment in the conclusions. So now I will present very briefly the results. Let me show here just the results of one of the specimens, because there are many simulations for several ratios GL1, also ratios of the bearing bandwidth versus diameter. So here it has been selected just a representative example, and we can see here in the simulation that the crack propagates from the center and then reaches the boundaries, and here there is the ratio between the maximum crack opening versus the characteristic length W1 at the end of the computations. So this is the curve of nominal stress, dimensionless nominal stress versus dimensionless horizontal displacement. There is a refinement of the steps just to capture accurately the maximum, and the nominal stress has been computed according to this formula used in the Brazilian test to calculate the tensile strength. So we verified that the maximum occurs for a crack opening smaller than W1. So the hypothesis by using the linear curve seems to be adequate. And now I show here the size effect curves enlarged for the several ratios under study of bearing bandwidth versus diameter. And the main important result is that there is a significant difference between the tensile strength inferred from the splitting test and the true tensile strength for ratios below 0.4. So this enlargement of the curves is important just to determine the precision of the method and for the correction of the values of FTS, as explained, because these values are very normal for the current mixtures of high strength or ultra high performance concrete. In particular, for the mixtures that originated this work, we would be here, and for ratios of bearing bandwidth of 4%, the error in the determination of the tensile strength would be around the 5%, and of the 12%, 13% for bands of 8% of the diameter. So it seems that maybe for the new mixtures, the conditions of the Brazilian test should be reviewed, because maybe this bandwidth is not admissible, but if they have to be used by any reason, because otherwise the test is very difficult to be performed, then it should be taken into account, this error, and correct the tensile strength obtained by using the iterative methods that I mentioned. And for this, analytical expressions of this curve will be provided in the future. We didn't have to include them in this presentation, but we are working on that. So just to conclude, I will say that indirect tests are commonly used to determine the tensile strength of concrete, as they are very easy to perform. The size effect cannot be ignored and should be taken, sorry for the misprint, into account for interpreting the results and for designing appropriate tests. Research is under development to extend the size effect curves of the Brazilian test for low ratios GL1 feasible for the new mixtures, and the difference between the tensile strength inferred from the Brazilian test FTS and the true tensile strength FT is significant for mixtures with ratio DL1 below 0.4, and the current experimental